Omar couldn't make this conference, so I've stepped in sort of with, I don't know, maybe a week or two's notice. But I'm going to maybe give a summary of some updates of what's going on in Omar's group at the moment. So forgive me if you've heard some aspects of this talk at other conferences, but hopefully there's something new in there that you can take away from today's talk. So we've been collaborating quite heavily with Richard Craster, who's just stepped down as the head of the mathematics department at Imperial, and he's putting more time into research these days. So great to have contact with him. But also some of you might know Damir Jurich from CNRS in Paris. So a lot of the interface tracking methods in today's talk are due to his group, with a collaboration with Hongik University in Korea through Sengwon Shin, and Jalal Shagai is another researcher in Paris. And it's not a pyramid. Well, it is a pyramid, but we're sitting down the bottom here. So there's an ensemble of postdocs and PhD students. It grows further and further than this, but some of the work presented in this talk is due to these students and postdocs. So Omar's goal is, it's ambitious, but it's to reduce the use of empiricism in simulations. And the reasons are, as we've seen even today in a lot of the talks, that you draw a parity plot of correlations and who knows where you end up. So the strategy for this is to couple an experimental program and a simulation program in the same research group. And hopefully these two aspects drive each other, but that's easier said than done. So the goal is that the simulation experts will gain ideas from the experimentalists, and each of them learn from each other. But yeah, it's hard in practice. So Omar sort of outlaid this plan. He had a big grant that's just finished up late last year called the Memphis Grant, and he's declaring no more empirical correlations. So you'll see from this talk how successful that was. So, but there's hope. We have a strategy going forward. So I'm going to talk a little bit about the front tracking technique that we've been using. So this is, you're about to hear from Stephanie about interface capturing methods, and I'm not sort of claiming that one is better than the other, but some of the difficulties that I experienced in my PhD research with interface capturing methods was if I used level set methods, I had to pay attention to mass conservation, and if I used volume of fluid methods, I had to pay attention to parasitic current problems, which blew up as I refined my mesh. On the other hand, there's this interface tracking paradigm, which goes back to researchers such as Greta Tryggvason and others. But there's been issues with this paradigm with parallelizing these codes. And so what Damir Jurich has been focusing on is hybrid methods that sort of capture some aspects of capturing, some aspects of tracking. And I just wanted to focus in on the single Navier-Stokes equation that we solve. Just look at the surface tension force to highlight sort of which parts come from capturing and which parts come from tracking in this implementation. And so the curvature field here is actually just calculated from the Lagrangian grid, which is embedded on the physical interface. And so there are stencils, kernels to calculate the curvature here in the surface tension force accurately. But what's interesting is that the Lagrangian mesh is used to define an indicator function by solving this Poisson equation. And then that indicator function is available on the Eulerian mesh, which you can use for interesting things. And the thing that it's used for in this implementation is actually remeshing the interface. And so what happens is that at a given point in time, if you decide to remesh your interface, which is sort of given by this traditional level set type color function thing here, but what you can do is you can look at the intersection of that contour with your Eulerian mesh and decide to place your new points on your interface where these intersections occur. And so that can lead to some ambiguities if you just have, say, a square, regular structured mesh. Say if your contour intercepted in this way, you wouldn't know exactly what the orientation to choose from these two options would be. And so the way around that is to chop up each of these cubes in a 3D simulation into tets. And then there's this tetrahedral marching algorithm, which means you can cut up your new interface without this ambiguity. So typically we would remesh the interface maybe every 30 time steps in a simulation. So it holds its structure well enough. And then the other thing that we get out of free meshing is we can deal with merging events. If you're trying to simulate coalescence, you have the level set function. So you can avoid sort of ad hoc cut and connect type methods that are traditional in tracking approaches. So this is what Ricardo, one of the current PhD students, generated with this method. It's a pulsed jet, and you can see even sort of on a commodity university cluster, you can achieve quite a high level of detail. And here's another simulation here of a Villemot jet. It's been downsampled the data by about a factor of 8, but you can see that the technique can capture quite complex things. So interaction between gas flow, liquid flow. We can look at sort of like non-Newtonian rheology, things like this. So you can see here just a breakup into these ligament structures, and then the instabilities that form, and the satellite droplets that are driven to separate by a surrounding gas flow. But this slide's more about sort of just highlighting some of the capabilities of this code. It's called Code Blue. One of the things we've found useful is the ability to snap to sort of quite complex geometries, because the solid objects are implemented in an immersed boundary type approach. And then as a user, you don't have to worry too much about the complexities of meshing these systems. You can just define primitives, but I'll talk about that in a moment. We've been looking at sort of multi-physics type problems, things with surfactants, heat transfer, phase change, and also going forward, there's a lot of interest in non-Newtonian fluids. We're interested in non-Newtonian spray systems at this point in time. We've got another postdoc who's looking heavily at turbulence research and how that transfers to two-phase flows with this code. In terms of parallelization, it's been tested on a Blue Gene infrastructure in France, but this is a low memory system. So you're looking at sort of, I don't know, each thread being accessed on the order of tens of megabytes rather than gigabytes of RAM. But Damir did a weak scaling study where you keep the local resolution in your subdomains constant, and you can see the speed up matches the ideal speed up until, I mean, this is 16,000 threads, but I think they were just limited by the infrastructure they had to test this on. So one thing I've been looking at quite heavily the last year is answering the question of how do we give all this power to undergraduate students who don't have a background in a research environment, so they're not exactly experienced with text editors, terminals, sort of heavyweight VTK graphics processing applications that we kind of take for granted in our daily work. So one thread of work that we're looking at is how can we make what's called a science gateway. So there's the community in the US around creating web applications and gateways to research codes. So that's something we're very much tuned into, and we're testing on a current batch of undergraduates at the moment. So the idea is, instead of seeing a text editor and a terminal, you get this friendly kind of widget interface with sliders. You can interact, see videos on your device. Maybe it's a phone or a tablet instead of conventional desktop computer. Today I'm going to talk about a few settings where we've sort of stress tested this code, and one of the simplest sort of ideal systems is that of emulsion microfluidics. And so this is a a system with low Reynolds numbers, our code better behave well for this ideal system. And so Liaz, some of you might recognize Liaz, but he's been looking at microfluidic applications. And here we've got an illustration of how simple it is if you have access to primitives in an immersed boundary method to construct quite complicated geometry without meshing. So you can say, I want a torus here, a cylinder there, I want a union or an intersection, which is quite powerful. You can also scan industrial STL files in this way to generate the required immersed boundary components. So what Liaz was looking at was this microfluidic system. I think the dispersed phase here is slightly more viscous than water, but the parameter that was varied was the flow rate ratio here of the dispersed to continuous phase. And you can see interesting things like this merging here, pinch off, and you can see that it actually re-merges. So there's a two-stage pinch off breakage process there that we found interesting. And then one thread of this work has been just comparing the experimental and numerical results one-to-one, looking at the agreement there. But we're interested in extending this to some biomedical type applications for the manufacture of double emulsions for encapsulation type applications. And so this was a study here where we have what you might think is 3 fluids, but we've just got sort of phase 1 and phase 2 in phase 1 again. But what would be amazing is if we could deal with n phases. So do have like a truly multiphase where multi is. So someone mentioned we have 1 to an infinity before, but if we could do 4 phases with all of the contact angle combinations and everything, that would be quite an interesting code to work with. I've been looking at this case where we've been firing droplets at each other. This was a bit strange. I didn't know how to initialize two spheres traveling towards each other. So I built the entire system with jets. It's way more complicated than it needs to be. But if I was doing this again, I would zoom in on the action here, which is the collision of 2 droplets. And so you can see that the phases automatically merge. So there is a parameter in there of sort of a threshold film thickness where below that we have instant merging. So I'm very much interested in thin film drainage problems, and Olivier mentioned yesterday this technique of having arbitrarily close interfaces. But here we have a parameter which controls the merging. But you can see we get interesting film sheet thinning here, breakup, holes, formation of holes, features like that. So it's quite interesting to use this tool to study the instabilities that form. And so one thing I could just make a point here that I had a look in the literature for multi-phase simulations for like spray systems and emulsion systems. And from a cursory glance, you can see that the system I'm very much interested in is this emulsion systems, or oil in water emulsions, but it's really hard to find simulations in the literature that use physical values for the physical properties. A lot of simulations here are sort of idealistic, intermediate type simulations, but predominantly spray systems rule the roost. So there are ways we can look at effects of mesh resolution, zooming in on sort of cusp-like features that occur when we go to higher mesh resolutions. But to truly attack this problem, you need to use a multi-scale approach and couple in information from film drainage, lubrication theory, fields like that Omar also has a background in. And so we're interested in, this is work we haven't actually done yet, but if you look at the collision of emulsion droplets or even spray droplets, the dimensionless group of importance is the Weber number. So we're looking at the inertia of these colliding droplets versus the surface tension force, which is tending to restore them back to minimize their surface area. So there's some great experimental data out of Delft, sort of looking at the first regime maps of this system. So one thing we're planning to do is stress test the code using this type of experimental data. So some other work that's been going on is moving towards surfactant systems. So I won't go through this in much detail, just to say that because we have an interface tracking method, it's quite natural to look at transport equations on this interface. So we can look at things with quite a straightforward equation. We can look at source terms for adsorption, desorption of surfactants to this interface, and so we can look at analytical expressions from the literature to look at what happens if you grow a sphere. Do you conserve your mass of surfactant, or if you load one side of a sphere up with a lot of surfactant and watch it equilibrate, does the time scale match the analytical expectation? Or if we have some information about kinetics of adsorption and desorption, how long does it take for a clean interface to reach saturation? So that's something that the group has been looking at. But if you apply this to a larger system, we can look at things like wetted wall annular film columns. So this system will have a gas flow coming from the bottom to the top, but the liquid film is just falling due to gravity. And so we can look at sort of qualitatively what does the difference what is the difference in the dynamics if we have clean interfaces or we allow some sort of presence of surfactants on the interface. And so Asen, one of the PhD students, has been tasked with regime mapping this problem in connection with some of the experimental data. And so there's this transition which is interesting from a rather sort of uniform falling interface here, but if you crank up the gas flow, you get wave instabilities forming and droplets breaking off, and you have this entrainment problem. And if this is an industrial reaction, you'll have hot spots in the small droplets that form, so your conversion rates will suffer. So we're interested in classifying this problem using that code. There are some nice mixing problems. So this was a demonstration of the fact that we can do moving solid objects with the immersed boundary method. It's still very much at a qualitative stage, so we haven't looked at the statistics of what's going on in the system with the evolution of this droplet size. Oh, this is a bubble size distribution, but we can start to ask design type questions. So this is a sensitivity study to the rotation rate here, and you can see if we hit 10 hertz and then step up to 11 hertz, there's a big change in the behavior. So the vortex will get sucked down here at 10 hertz, but at 11 it will start interacting with the blade, and so we have this instability in this system. So I got frustrated with this code because I had to wait a long time to get a result. And so this was an example I showed where I had to wait 2 days here. So what we were doing was just introducing some water into a pipe. It should be a simple problem. And then there's this sheet that forms here when it collides with the solid. But I ran a very low fidelity volume of fluid method, and I got a result in less than 1 minute using an open source code. And we sort of thought, if you were trying to make a design decision, would you want to wait, if you're a junior engineer or something, for 2 days to make the call on something, or could you have enough information in this low fidelity model to come to the same conclusion? And so one thing we're looking at now is, I guess we have two strands, is what do I do if I want to optimize a very expensive model, and how can I increase the speed of my very expensive model? So one thing we're looking at the moment is surrogate model optimization. And so this is where you have a gradient-free optimization strategy. So say you had a budget of maybe 50 or 60 calls to your simulation. The question we're asking is what's the best strategy for choosing the points in parameter space to simulate. And so what we're working with some input from a data scientist, Indranil, is how do we update our surrogate model of optimization strategy as we go. So we might run 10 simulations, update our surrogate model, and then query our surrogate model for the next simulation that we should run. So we don't really have a good problem to throw at this yet. So I chose this toy problem of just flushing out a viscous pipe as mainly a strategy to see if we could connect all the required components together. So we have an open source volume of fluid solver here, but we're also using a lot of open source Python machine learning and optimization libraries. So this was more of a capability building exercise, but we're in the process of selecting some sort of more relevant problems. But you can see here that we can map out sort of the parameter space. So we did a search in Reynolds number and viscosity ratio to work out if I had to flush out this pipe, which parameter choice would leave me with the minimum amount of product in these corners, because this might be a problem if say you're in a food or a consumer goods manufacturing facility and you need to use the same piece of equipment for multiple processes. If you're cleaning it out, you don't want to contaminate the next batch of product with contents from the previous batch. And so by looking at the various sort of the time series of how much residual product there is, we can just trace sort of which was the optimal set of parameters for cleaning. But you can see there's not a lot of spread here in the result. And then if you map out sort of the optimal solution, there's not much of a pattern there in terms of sort of you can't really draw contours of good and bad solutions. So we're looking for sort of prototypical problems that we can use to learn how to do this type of optimization with multi-phase systems. So this is another thread that Aditya Karnik, another postdoc, is working on. But Omar's very much interested in wave features that form on the interface. This is a free surface with a liquid gas system, and so there's been sort of some work to look at validating compared to the experimental literature. The statistics of these wave features that appear on the surface when you have a driving gas flow. But one thing that Aditya is working on is this whole idea of can we run DNS simulations at this stage just for a single phase flow and learn enough information from them to correct some of the terms that we use in our large eddy simulations. And so he's been working on this neural network approach where at the moment we're just learning from single phase DNS data. So his training studies are done with on the order of 4 million cells. But then if we learn from these training sets how to implement subgrid viscosity type corrections in a large eddy sense, how can we reduce the cost and the cell count in these lower fidelity simulations, but still retain the information that we learn from the detailed DNS simulations. So this is very much early stages, but at the moment he's claiming like a increase in speed for about a factor of 2. And this is a sketch of I think the model that is used to look up for the turbulent viscosity correction, and you can see it's almost just like curve fitting at the moment. So he's claiming that his cheaper machine learning large eddy simulation will give equivalent results to the more expensive direct numerical simulation. So I think I'll just finish up here and say that we very much are based around this multi-scale approach of choosing problems at the small micro scale. So I've shown some microfluidic type problems, but also very much looking to push this code to solve industrially relevant problems. But this is a challenge. I mean, this mixer that you saw is on the order of maybe 10 centimeters by 10 centimeters, and getting that behavior to work at the scale of 1 meter by meter is still prohibitive for us. So this is one of the reasons why we're looking at hybrid methods between sort of moderate and high fidelity simulations and what input we can get from the machine learning literature. Also, we've been using this hybrid level set front tracking method, but for certain applications, interface capturing I've shown is something we also still use, and very much so. And so I think I've pretty much said this, but for me, I don't have much time as a postdoc, but we're trying to optimize the use of large-scale simulations with finite resources, finite time, and really the objective is just to minimize the time it takes us to get the results so we can make interesting and sort of correct decisions. So that's it for this talk. So thanks. Yeah.
All right, so we have about 5 minutes for questions.